Good morning to all. In this video, we are going to see the subject named Linear Integrator Circuits, in which we are going to see the topics from Unit 2 titled Applications of Operational Amplifiers. I am Divya, working as Assistant Professor, the Department of ECE, R.M.K. College of Engineering and Technology, Chennai. To introduce, the op-amp has a large number of applications. Some of them are linear applications and some are non-linear applications. Linear applications means they are the circuits where the output signal varies with respect to the input in a linear manner. Non-linear applications, on the other hand, the output of those circuits vary non-linearly with the input characteristics. Other than this linear and non-linear application, we have some basic op-amp applications such as sign changer, scale changer, phase shifter, voltage follower. Out of these basic applications, we are going to see the phase shift circuits. And this diagram shows the circuit of a phase lag circuit. Here we can see the inputs of inverting and non-inverting terminal are tied together and given with a single input, that is, it is working in a common mode signal, and the value of RF feedback resistance is equal to R1, and to the non-inverting terminal we have R and C connected to that. So the voltage available at the pin number 3, that is non-inverting terminal, is VA. Since this op-amp has been given with inputs at both the terminals, that is inverting and non-inverting terminal, first let us consider the output due to the inverting input. So considering this as an inverting amplifier, the formula for the output is V0 is equal to minus of RF by R1 into input. This is the gain of the inverting amplifier circuit. Here the value of RF is equal to R1. So when we rewrite that, we get V0 is equal to minus of R1 by R1 into Vi. So they get cancelled. We got V0 is equal to minus of Vi. So output due to the input present at the inverting input terminal is minus of Vi. When we consider this circuit as a non-inverting amplifier circuit, the output V0 is equal to 1 plus RF by R1 into Va, that is the voltage available at the non-inverting input terminal. This is the expression for the output. Here RF is equal to R1, so when we substitute RF equal to R1, we got 1 plus R1 by R1 into Va. They get cancelled and we got V0 equal to 2 times of Va. This is the output voltage available because of the input present at the non-inverting input terminal. Now our job is to calculate the value of Va, that is the voltage available at the non-inverting input terminal. So while calculating the value of Va, that is the voltage available at the non-inverting input terminal of op-amp, that is V0 equal to 2 into Va. Va is the voltage available across the capacitor C. So which means current through capacitors into the reactance of the capacitor. Current through capacitor is Vi divided by R plus 1 by j omega C into reactance of capacitor, that is 1 by j omega C. When we take LCM, we will be getting like this. J omega C will get cancelled and we got Va is equal to Vi divided by j omega RC plus 1. When we substitute the value of Va, we got in the expression for V0, we get V0 equal to 2 into Vi by 1 plus j omega RC. So when we combine both the input voltages, that is input present at inverting input terminal and input present at non-inverting input terminal, we got Va is equal to minus of Vi plus 2 times of Vi by 1 plus j omega RC. This is because of the input present at inverting terminal. This is because of the input present at the non-inverting input terminal. When we substitute in terms of frequency in order to analyze the phase characteristic, we got V0 of j omega is equal to minus of Vi of j omega plus 2 times of Vi of j omega by 1 plus j omega RC. Let us take V of j omega common and combine all the values, we get output by input, that is our gain is equal to V naught of j omega by Ba of j omega, that is equal to 1 minus j omega Rc by 1 plus j omega Rc. When we calculate the phase angle of the above expression, we get theta is equal to tan inverse of minus omega Rc. This is because of the numerator component, minus of tan inverse of omega Rc. This is due to the denominator component. So when we rewrite, we get minus tan inverse of omega Rc minus tan inverse of omega Rc, that is equal to minus 2 times of tan inverse of omega Rc. When we substitute omega equal to 2 pi f and rewriting that, I get minus 2 into tan inverse of f by f naught, where f naught is equal to 1 by 2 pi into Rc. So theta value, that is the phase angle, what we got is minus 2 into tan inverse of f by f naught. Let us substitute different values of f and we will find the answer. For theta, when f is equal to 0, we get theta equal to 0. And when f equal to infinity, we get theta is equal to minus 180. When we have f is equal to f naught, they both get cancelled and we will be having minus of 90. So when we draw the phase circuit for the above said expression and magnitude circuit for the above expression, will get like this. Here we can see when f is equal to 0, phase angle is 0, f is equal to f naught, phase angle is minus 90, f is equal to infinity, your phase is minus 180. So from this we are clear that as frequency increases, phase lag also increases. Thus the above said circuit work as a phase lag circuit. Thank you all.